Okay, so graphs of polynomial functions. So reminder that when we graph polynomial functions, a big part of what the graph looks like is going to be caused by the leading coefficient and the degree of the polynomial. And so we're going to take a look at each of those things to know what happens. So we're going to be talking about end behavior again as far as that goes also. When the degree of a polynomial is odd, the end behavior or the ends of the polynomial are always going to look like it does here in figure 4.31a. They're going to look like that. Not necessarily, and you can think of this as, you know what happens when we take our window and we just zoom it way out, right? Okay? We don't see what happens in the middle, do we? Okay? So think of this as a window that's zoomed way out, and so really the only thing that matters is what's happening on the ends. So an odd degree polynomial, they're either going to look like this one does here, or they'll look like the what? The opposite if it's negative. Okay? All right? If they're even degree, then they're going to look like these, which on the ends they look like a quadratic. Right? Either they both go to positive infinity or they both go to negative infinity. So when it's an odd degree, one goes up, one goes down. Okay? If it's even degree, they either both go up or both go down. Okay. As far as continuity goes, every polynomial function is continuous, which means what? Okay. It continues, it does. Right? And it never stops. There's never a break in the graph. It always starts from negative infinity for x values and goes to positive infinity for the x values without any break, gap, or anything in it. Okay. End behavior, we just talked about that again, depends on what happens then also. The end behavior is what's it doing on the ends. So as x is really, really small, is the graph going to positive infinity? Is it going to negative infinity? Is it going to some constant? As x goes to positive infinity, is it going to positive infinity, negative infinity, or some constant? Okay. When we talk about end behavior, we talk about that. And it all depends on whether the degree is odd or even. Okay. So here is what's going to happen generally with the graphs. The end behavior. If we have an even degreed polynomial with a positive leading coefficient, then the general form of the graph is always going to look like this. Both ends of the graph are going to go to positive infinity. So as the graph goes to negative infinity, it goes to positive infinity, it goes to positive infinity, y goes to positive infinity. Okay? The graphs are always going to look like this on the ends. Okay? In between, there might be a whole lot of different things that happen in there. Okay? Just like what we see here, that with this fourth degree polynomial on the left here, and this other fourth degree polynomial, those both go to positive infinity, but what happens in the middle there is different. Okay? Still doesn't affect it. Emily? Didn't I give you one for this chapter? Oh, see, apparently I don't think you need one. You're so smart, you don't need one. Okay? All right? If the leading coefficient is negative, then instead of them going to positive infinity, they go to negative infinity on the ends. That's the end behavior. If the degree is odd, positive leading coefficient starts at negative infinity and ends up in positive infinity as it goes across. If the degree is odd, has a negative leading coefficient, starts at positive infinity, so it starts in the the second quadrant, ends up in the fourth quadrant. So you can kind of think about it as quadrants also. Is where is it in each quadrant? Okay. So these are the general shapes of the graph given whether the degree is odd or even and the leading coefficient is positive or negative. All the graphs as far as on the ends will always do that. What's in the middle around the x-axis, okay, could do a lot of different things could happen in there. But when we're looking at end behavior or how do I know whether it's odd or even degree, all I have to do is look at what happens on the ends. Are they going up, going down? Are they going opposite directions or not? With intercepts, we know that whatever the degree is of the polynomial, that it could have that many x-intercepts, but it always only has one y-intercept. Okay. There could be at most n x-intercepts, but only one y-intercept. Right. Yesterday or the other day we were talking about multiplicity. Here's the rules of multiplicity again. Multiplicity is based on the factors. How many times is it a factor? Okay. Also goes along with the zeros. Okay. If we look at this graph over here, this graph has 3 zeros at -3, -1, and 1. And their multiplicity of them depends on, I can think of it as two ways. I can think of it as what the graph does. If it behaves like a quadratic, okay, so it touches the x-axis and goes back the direction it comes from, it's even multiplicity, 2, 4, 6, or 8. If it goes right through the x-axis, just cuts right through it, then it has degree 1, or a multiplicity of 1. And if it bends, like this one does here, then that tells me it's going to be odd and greater than 1. And we can look at it this way also as the factors. Okay? Here we have the factors. Our 0 at -3, when I write it in factored form, that factor has degree 2. X plus 1 in factored form has degree of 1. And x minus 1 has a degree of 3. So the degree of the factor and the multiplicity are the same. So notice, what is the degree of this whole polynomial here? It's 6. Okay. Notice what happens when I add up the multiplicity. It's 6. They're the same. The degree of the polynomial and the sum of all the multiplicities should be the same. And multiplicity depends on what happens on the graph. Does it go through it, right straight through it? Does it bend when it goes through it? Or does it touch it and go back the other direction? Okay, so we've got these. First, I asked you to figure out these 4 questions. Why does the graph of every polynomial function have a y-intercept? How come? Garrett? It doesn't necessarily start on the y-axis. They go in opposite directions all the time. Okay, that could be part of the reason. It just does. Okay. Okay, x goes from negative infinity to infinity. Is there ever any breaks or gaps in it? No. So the graph, the reason it does is because it's continuous. Why does every letter B asks, why does every graph of a polynomial only have one y-intercept? Max? Okay. All right, it wouldn't be a function then, right? Failed the vertical line test, so it wouldn't be a function if it had more than one y-intercept. Letter C, why is the y-intercept of this a sub 0? All right, go ahead, Max, you're on a roll. Okay, that's the constant, but why is that the y-intercept then if that's the constant? Savannah? Let me ask you this. What's the x value for the y-intercept? There is one. It's 0, right? So what happens if I put 0 in for x? What do I get? 0. So if I put 0 in all these other ones for x, that means all the rest of the terms are going to equal 0, and the only thing left then is a sub 0. A, B, C, and D, which ones have an x-intercept? Hopefully you don't go by what the things I put up there are, because they're not for that reason. Which ones have an x-intercept? Does A? Okay. How about B? No? Why not? Okay. All right, because that plus 9 means it's going to be shifted up 9. Okay. All right, how about C? Yep. Okay, because when I put in 0, I get 0, right? How about letter D? Okay, why not, Maria? Okay, all right. Very good. For letter D, it's going to be upside down because it's negative x to the fourth. So that means it's going to be shifted down and it's going to frown. And those two things together just don't work. Okay. So B and D do not, because B is shifted up. And D, it frowns and it's shifted down. So if it does have x-intercepts, we can usually factor it, right? Not always, but quite often we can. All right, so let's look at the examples. So multiplicity. All right, I like to make a table. All right, my table says list the zeros, what the graph does, and so then what is the multiplicity then for it? So in this problem, nope, okay. I have zeros where? Negative 1, 1, and 3, right? Okay. So at negative 1, what does the graph do? Okay. Does it go through it? It does, but when it goes through it, it does what? It bends. All right? All right. I see some of you are graphing that. Do you want me to wait and let you finish graphing it first? All right. I'll hold on a second before I go any further with this thing. So if we have zeros at -1, 1, and 3, first of all, what's the degree of this polynomial? 6. Okay? Which means either the graph is going to go, both of them are going to go up, or they're both going to go down. Okay? It's either going to smile or frown when we look at the ends. Okay? When you think about the, whether you got that, the good showing with your mouth. It's like, like the Joker, right? Okay? Now, so it's degree 6. That means it's going to either go up or down. What about the leading coefficient? Is it positive or negative? If I put all these together, these x's together, is it going to give me a positive number or a negative number? Okay. All right, it's going to be positive. So that means that my graph is going to start up here, and it's going to end up there. On the ends, it's going to smile. Now, at -1, because it's degree 3, that means when it comes down to -1, it's going to bend going through the x-axis. At +1, the degree there is 1. So that means when it comes back up through +1, it's just going to go through it, right straight through it. At +3, it has degree 2, which means that it's going to act like a quadratic function. So that means that it's going to come back down, hit the 0 there, and go back up. And so I have my general shape of my function. So at 1, it goes through, or sometimes they'll say crosses it. And at 3, it just touches. So if it bends, that means the degree's got to be odd, greater than 1. In this case, it's 3, because that's the power of the factor. If it goes through or just crosses, it's always just 1. And if it touches, that means it's going to be even. In this case, it says the factor is squared, so that has a multiplicity of 2. And we notice that all 3 of these add up to the degree of the polynomial. So the best way to do that is always just make a chart like that. Keep track of what happens. And I don't know why I redid that. Hey, look at that, I did it twice. Let's delete that page. There we go. All right. Okay. Extrema. Okay. A local extrema is talking about max and mins. Okay. Your graph could have numerous max and mins. All right. Now, I know that the degree of this polynomial I've just drawn must be at least 9. Okay? Because it says a polynomial of degree n has at most n minus 1 local extrema. At most. So the degree of this polynomial would have to be at least 9 because there are 8 different max and mins. Okay? If it looked like this, I know the degree must be at least 4. Okay? Could be greater than that because there could be some complex roots. Okay? But I know it's got to be at least 4. Okay? The number of points of inflection would be 2 less than the degree. So there are at least n minus 2 points of inflection, because this one has 2 points of inflection. They'd be here and here, remember, because there's always points of inflection are always halfway between or between the max and mins, because that's where it changes from being on concave up to concave down. This one here has a lot of points of inflection. There's one here, 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 down here probably, about there, and about there. 2, 4, 6, 7 points of inflection with a degree at least 9. Okay. All right, complete graphs. Okay, did you graph this? How many of you graphed it already? Okay. Everybody graph this. We want the smallest window it'll fit in. Talk about our window. Now, first of all, there's one number from my function. I know one number for sure. What is it? Okay, the y-intercept is negative 70, right? So I know that my y-min is going to have to be at least negative 70. Okay. Now, what's the degree of this polynomial? Okay, it's 4th degree polynomial. Leading coefficient is what? Okay, so it's positive, right? So that means the graph of this polynomial has to look something like this. Positive leading coefficient, even degree, the degree is 4. So it could have at most 3 local extrema, at least 3 max and mins, okay, total. So when I graph it then, I should be able to see all of that. Can I see it with what graph I have here? No. Okay. All right, we know that I've got to go down to at least negative 70. So let's go negative 100. I have no idea. I'm just guessing. All right, now let me graph it and see what happens. Okay? All right. Can I see all of the possible aspects of a 4th degree polynomial? Okay, it looks like it smiles from the ends that I can see, but I only see one local extrema. Okay? So I got to look for more. So what do we need to do? Make my y max bigger, okay. So where should we go with that, Savannah? Okay, so you went to 70. All right, and we'll go by tens. All right. Okay, let's see what that gets me. Oh, did you guys see what I saw? Okay. What? Oh, there's more to the left. There's this little piece here over the left-hand corner. All right, but still, by the look of the graph, it's curving, isn't it, as it goes up to the left. So there's got to be more there. So I've got to go higher then, don't I, for my max. Okay? So we need to go a little higher. So let's try. So from this, looks like we need to go higher and we need to go to the left, right? Okay? So let's go to the left. Let's go to negative 10, see what that does for me on my graph. See, I made mine a little bit bigger. And let's try 100 here. Okay. Now, can we see everything we need to see there? We see 3 extrema. We can see that it's opening up on both ends or going up on both ends. So, is this the smallest window I can make and still see that? No, it's not. Okay? Because I can actually shrink it which way? Okay, the x's. All right. So I could go to like negative 8 and 3, right? Let's see. All right, I can see everything there, and yep. All right. So we want to, oh, I changed it a little bit different. Negative 11 to 3, negative 100 to 100. So something close to that. Yours isn't going to be exactly the same as the ones I choose, but this is very close. This will allow us to see the whole graph. And when we talk about a complete graph, we're talking about seeing all the different aspects you can of the graph. So your graph look like this, right? Now you have to be able to see the fact that there is what? There are, no, two local extrema. There is a max and there is a min. Because if you look at this graph, you can see that it does. It rises up, comes back down. It looks just like that one we had in that one problem a while ago, right? Okay. If you didn't zoom in far enough, you couldn't see it. Okay. So here's the window that I used. Negative 3 to 5 on the x, negative 2 to 3 on the y. Now here's the thing. Sometimes with these situations, if you go too small, you actually can't see it either. Okay? It loses the aspects. So you have to be careful what you're doing and what you're looking for. So if I have a degree 3, I should be able to see 2 extrema. Okay? Is that always the case? No, because if I put x cubed up there, it doesn't have any extrema. Okay? But remember, that is at most. It doesn't mean it's going to have it for sure. It means at most. Batteries work? Oh, good. Okay. All right. Complete graphs. When we're talking about a complete graph, then still, we need to know two things. What's the degree? Or I should say three things. What's the degree? What's the leading coefficient? And how many extrema are there? Okay. Those three things are what's important. If the degree is even, on the ends, the graph better go the same direction. Okay. If the degree is odd, on the ends, the graphs better go opposite directions. Okay. All right. One's got to go up and one's got to go down. Okay. So here, for problem number 4, they gave you this. The function is 0.02x to the fifth. Do I care about anything else? Absolutely not. The only thing that matters is the first term. Is the leading coefficient positive or negative? Is the degree even or odd? This is a positive leading coefficient and an odd degree. That tells me that the graph has to look like this on the ends. And to look at this graph, they're both going the same direction. Okay? So which end is wrong? Okay, the left side. Okay, I know that because it's got to start at negative infinity and end up at positive infinity because the leading coefficient is positive, the degree is odd. So this graph has to come back down here somewhere. So it wasn't a complete graph. Okay, it says determine if the graph is complete. Okay, and the answer in this case is no, that was not a complete graph because of the leading coefficient degree, it has to go back down towards negative infinity to the left. That's a pretty color, isn't it? Looks like the NFL all month of October. Okay.